Welcome, everybody. So first of all, I'm Ion Stoica. I'm the director of the lab. And I just want to ask one question. How many of you are here for the first time at a RISE lab or AM lab attending a retreat? Okay, so quite a few. So we are going in the first 50 minutes, we are going to give some overview presentations about the research in the lab, the progress we've done since the first retreat, which was in January, so we are 4 months later. And after that, we are going to have a set of talks on particular systems, algorithms we've been developed. So RISE Lab, RISE again, stands for Real-Time Intelligent Secure Execution. Includes people from various areas which come together to solve the problems we targeted for ourselves. So includes people from system, AI, security, and architecture. And here are the faculties who are part of the lab. And we are funded by some great companies here, 11 companies, founding sponsors. And they will make this possible. So first, let me start with the retreat goals, especially for new people who are attending for the first time. So the retreat goal is to foster collaboration between the industry, our industry partners, and students and faculty. And feedback, okay? So what collaboration means? Basically, talk with students, talk with us. We have 2.5 days, so it's enough time to mingle and talk, ask questions, and provide feedback. And here where actually we start and continue the existing collaborations. During these retreats, it represents the best events we have to foster this collaboration. Like I mentioned, the other goal is feedback. We present our visions, our latest results and thoughts, and we are really looking for you to provide detailed, blunt feedback. And finally, it's about bonding. We are just 4 months in a 5-year journey, so let's know each other better. So the goal of the RISE Lab is to develop open source platforms, tools, and algorithms for intelligent real-time decisions on live data. And the next few slides, in the first retreat, we give an overview of our research vision and agenda. Here, I'm going to talk a little bit about how we are conducting research in the lab. So one, because we are doing AI now, and as you know, in many of these AI algorithms, you have to trade between the exploration and exploitations, looking at new things and doubling down on existing things. This is what we do. So that's part of our research style. So we trade between exploration and exploitation. Exploration meaning that we try new ideas. And at the beginning of the lab, it's a bigger weight on the exploration to try new ideas. And then its exploitations is that out of these ideas we double down on the most promising ones. What does it mean, doubling down? For instance, we build artifacts, real systems, like Apache Mesos, Apache Spark, RISC-V. And we have indirect impact, like the work was done by Rashmi had a big impact on pushing the Erasure codes in the new version of Hadoop distributed file systems. During this retreat, you are going to hear a bunch of presentations about many systems. And many of them are, they are falling in the exploration, on the exploration side. But we have a few of them on the exploitation side, right? So there are these few systems we are already decided to double down and to build real artifacts. Okay. One of the things we are doing, at least in these early stages, last time at the last retreat, I presented you a stack, secure real-time decision stack. And a lot of work is within that stack. I'm going to talk a little bit more about that later. Systems like Clipper, Ground, Fluent, Opaque, and Ray. But we also, right now, we are exploring outside the stack. So it's again, the stack is kind of only an assumption of our view of the world. But that is bound to change as we understand more and we do more work. We also do quite a bit of work in the context of Apache Spark, Drizzle, and Tegra. And notice that Apache Spark, it's actually can be part of our SRDS stack. So these two are not conflicting. And also we are doing some work really outside the SRDS and Apache Spark. You are going to hear about like Dialog, Netcache, and Pyren. Another very important aspect of our research is that most of these projects are multi-area collaborations. And here are a few examples. Ray and Pyren. It's AI and system students collaborate to drive these projects. Opaque, it's AI, security, and systems. Cyrus is systems and architecture. And many students are co-advised by faculty from different areas. So we really are taking a very holistic approach in addressing the problems and the challenges we set. The other interesting aspect is that actually the users of the systems, they design the systems. Like for instance, in some cases, the AI students design the systems they are going to use. And as you know, the user is the best position to specify the requirements of the systems they are going to use. A tenet of the labs at Berkeley is a strong collaboration within the lab. But what we are going to try to do in this new lab, in the RISE lab, we also are going to be more aggressive in seeking collaboration with other labs at Berkeley. And there are many great labs at Berkeley. So one, it's Berkeley Deep Drive. And for that, we already had a one-day mini retreat between RISE Lab and Berkeley Deep Drive. So they are, that's a picture from this mini retreat. Berkeley Center for Computation Imaging. We are already having a project we are developing in collaboration, Pyren. I'm going to talk a little bit later, and you are going to also hear a talk in the next section. And BEAR. Berkeley Artificial Intelligence Research, and several of the faculty members several of the faculties in the RISE lab are also members of BEAR. So we are really looking to collaborate very strongly and either collaborate to develop artifacts or to use each other results, right? Like for instance, Berkeley Deep Drive may use some of the systems we are building. And we may use some of their data and the application to validate and to evaluate our systems. So next I'm going to give a short overview on a few system projects. And then Raluca is going to give an overview on security work and Michael Jordan on the AI ML work. And there are many, many systems. So what I'm going to focus, I'm only going to focus on a few systems. That is systems which have been released or are about to be released. And systems we are actively working on, but because of the constraints, time constraints, we couldn't have talks on these systems, okay? So I'm not going to touch the systems who are not going to be released or they haven't been released, and for which we have a talk during the retreat. So if you remember from the past retreat, and if you look in also in the draft we sent to you, a Berkeley view on systems for AI, one of the main goals of these systems is to make the prediction, to make decisions, to take actions. So, and what are the desirable attributes of these decisions? So we identify a few of them. We want the decision to be intelligent. We are talking about complex decision in uncertain environments like fraud detection, medical diagnosis, detecting cyber attacks. We want to be able to render these decisions in millisecond level granularity in a dynamic environment on the state of the environment, which is just seconds old. We want this decision to be robust with respect to the noisy inputs, failures in the systems, and unforeseen inputs. We want the decision to be explainable. We want them to have the ability to explain what is in the output trigger a particular decision, in particular non-obvious decisions. And we want, of course, to be secure, the decision to be secure to ensure privacy, confidentiality, and integrity. And these are the systems I am going to talk briefly about: Ray, Clipper, Pyrene, Ground, Drizzle, and Tegra. And they have a check mark. What of these attributes they primarily target. So it's again, this is only what they primarily target. Each of them will have a component about security and so forth. Raluca is going to talk more about it. So this is our secure real-time decision stack, or SRDS. And here we are going to talk many of these systems you see on this, in this stack. One of the first systems you are going, the first talk will be about Ray. And Ray, it's with orange here. I am just showing what are the components of the stack which Ray is touching. So it's also both touching this Rice microkernel, which is supposed to be a very flexible and highly performant execution engine for parallel applications, and the Ray itself, which is an application framework. So Ray targets this next generation of AI application, in particular targets the reinforcement learning, which enables agents to learn by continuously interacting with the environment. And the system we built to support these applications has to be flexible to support dynamic arbitrary task graphs, to have high performance, to be able to run millisecond latency tasks, and to handle millions of tasks per second, and also very easy to use. In particular, easy to parallelize Python code, since most of the AI researchers and practitioners, they write and develop their algorithms in Python. And I'm very happy to say that we are just announcing the release, the very first release of Ray today. So it's out there, so you can start playing with it. The second system I'm going to talk about is Clipper. So Clipper is a model serving. So it's filling this gap between training the models and actually serving these models, making predictions, inferences, decisions, taking actions for the end users or agents. And again, Clipper, it's flexible. It provides a uniform interface across models, so you really can develop models in many frameworks like Spark, TensorFlow, Scikit-learn, MXNet, and things like that. And also is very flexible in terms of controlling the latency accuracy trade-offs for the queries and the responses. Has high performance, provides prediction caching, and you can have ensembles and cascading models, which will allow you to make this trade-off between accuracy and performance, and computation resources as well. And like I alluded, it's easy to use. It supports, in the first version, it will support Spark and Scikit-learn out of the box. It only requires a dozen of lines of code to add new models developed with other frameworks. And it's also targeting the model lifecycle management, which is, it's one of the most difficult parts once you deploy a model, right? And this is also going, it's released today. So this is another system you can start playing with it. Next one is ground. So ground, it's already, from the beginning, it was an effort between Berkeley and a few other companies, including Capital One, one of our founding sponsors. And ground, it's playing the role of, provides a functionality of a central repository for models, APIs, and it aims to capture the context in which data gets used and produced. There are two primary use cases we are targeting initially: global data inventory, to track the data lineage, models, and can be used for security audits, and also continuous integration for AI. And this will be a talk you are going to hear tomorrow between Ground and Clipper. So this is one of the first instances. You'll see how two of our systems we developed are used within the stack. And this is about, maintaining the versioning of the code of the model, parameters, tests, statistics, and so forth. So you can always go back and deterministically replay to, some prediction inferences based on a particular model and its associated parameters. So this is not released yet, but the release is imminent. We are expecting a release within the next week or so. Next, I'm going to present two projects we are doing in the context of Apache Spark. And this is the Apache Spark stack with a Spark Core and Spark SQL, Structure Streaming, MLlib, GraphX, and Spark R as libraries targeting different workloads. And Drizzle is focused on dramatically reducing the latency for streaming by more than one order of magnitude compared with existing structured streaming implementation. And using a variety of techniques, group scheduling and shared variables. So here it's a plot, and again, it's some millions events per second on the x-axis, the median event latency on the y-axis, and here for the 24 million events per second, you can see that compared with original Spark, you get 15x lower latency, and also compared with Flink, which is a system which is built from ground up for streaming. So provides an improvement more than 2x in this case. And Drizzle is gradually being implemented in Spark, rolling into Spark distributions. The other system is Tegra. There are many systems, graph processing systems. And what Tegra the problem Tegra tries to address is basically making queries on arbitrary snapshot in the past. Like, what was your friend's network, in December 15, 2015, okay? Also, it can compute the characteristic of the graph's connectivity, how it evolved over a window. And this is, we have an implementation on top of GraphX. And it also provides comparable or better performance than differential data flow, which is, again, a system which was built from ground up for this time-evolving graphs. And it's faster and requires less storage than GraphX, which is a library on top of Spark to support graph processing. In terms of computation, it's 2x faster. In terms of memory usage, storage usage, it's over 5 times faster, which means that on the same cluster, you can fit in 5 times bigger graphs. We are planning here for a fall release. Finally, PyRAN. This is serverless scientific computing, and you are going to hear a talk about this. It's the second talk in the first session. And this really is providing the Mac functionality at very large scales to Python users. And it turns out that this simple model is very powerful, and it helps to solve real machine learning or vision problems. It's a collaboration between this BCCI and Rice Lab. And just to give you a sense, I stole this graph from Eric's talk. And this is a number of workers. Today, it's implemented on deploy on Amazon AWS Lambdas. But every cloud provider has something similar, like cloud functions, and in both Google Cloud and Microsoft Azure. And these just basically show how it scales the computation capacity in terms of teraflops with a number of workers, number of lambdas. So you can get, in this case, almost scaling linearly up to 45 teraflops. And this actually was the first system was released. It was in March 17 this year. March this year, sorry. Actually, now I think we are at the release 0.2. So things progressing fast. I also want to address one natural question many people will have. When you look at these projects, it's kind of reasonably, there is some overlap between them. And I just want to say, what is the overlap and why is this overlap? So for instance, if you look at PyRAN versus Ray, it has a similar feature-based abstractions and does target the machine learning and AI communities. However, Ray focuses on fine-grained dynamic tasks, millisecond-level tasks, like I mentioned, while PyRAN focuses on easy of deployment. It's a serverless deployment, and for that, it's leveraging AWS Lambdas. But it's much coarser-grained tasks. Fluent versus Ray, both of them target fine-grained distributed computations. However, Ray provides a unified feature and actor abstractions targeted for Python users, at least in the first iterations, while Fluent provides a C++ data flow abstraction, very efficient and high performance. So it has more a traditional distributed system focus. Cyrus versus PyRAN, they are similar in that they both use a serverless architecture. PyRAN leveraging existing services like Lambdas and S3 to share the data, while Cyrus implements its own memory storage, and then therefore it can provide much fine-grained these Lambdas executions. They are called, I believe, micro Lambdas. And finally, Ray versus Synchronos, they both parallelize GPU-based training. Synchronos focuses actually on parallelizing one popular library, Thanos, on a single server with multiple GPUs. The library works well on one GPU, so Synchronos is parallelizing into multiple GPUs, very efficient parallelization, while Ray parallelizes multiple libraries across multiple machines. But to do that, it has to pay the cost of serialization deserialization, which Synchronos does not pay. So why we do that? Well, because this enables us rapid exploration, right? We are going to try different angles to solve the same problems. And this is the fastest way to learn and hopefully to inform the design of the existing and of the new systems. I'm going to end very soon. So, the main ingredient and part of the success of the lab is people. It's more than that, it's students. And I'm happy to say that this year we had a fantastic recruiting year for new PhD students. It actually seems that it's the best in memories. Typically, a good year from the people we make offers to, we get 50%. 50% is a good number. Again, we are competing here with MIT, with Stanford, CMU, and others. So getting 50% is a pretty good from the people we made the offers to. And here, what happened this year, AI absolutely killed it, 86%. So Mike can say, probably, I'm not sure was ever. OSI networking was 75%, and that because it was a little bit skewed on the negative side because there are two, in networking, both Sylvia and Scott, and actually Vern, 3 of our networking faculties actually are going to be on leave next year. And security 60%, which again is great. It's again a fantastic number. Also alumni, Rashmi, she's going to give a talk tomorrow. She's going to accept the position to CMU, computer science. And Shivaram, sorry, it should be SH, which many of you know him. He is going to decide between the University of Wisconsin and University of Chicago, and he cannot be with us today because he's now at the second visit to these schools. So finally, agenda and logistics. We have several sessions on systems, machine learning, and AI and security, which are typical talks, 15 to 20 minute talks, unless otherwise specified. And then in addition to that, we are going to have today, as today's dinner, breakout sessions. We are going to largely ask you for feedback on the draft we sent to you, a Berkeley view on systems for AI. And we are going to designate people at every table to take summaries and present them tomorrow morning. And I want to, if you have any questions, please don't hesitate to ask our wonderful staff, which makes all this possible. Kat, Boban, Carlin, and Shay. So with this, I thank you, and I hope that you are going to enjoy and have a very productive retreat. Thank you. So next will be Raluca, who is going to provide an overview on security in RISE Lab.
Okay, hello everyone, welcome to the RISE Lab retreat. So I will give an overview of the recent efforts in security. And pretty much everyone in the lab is involved in security or interested in some aspect of security. And that's because of our very collaborative nature. So really coming together from security systems and machine learning and working together. And the same for our sponsors. We heard from almost every one of them various security issues that they're struggling with. All right, so what kind of security threats do we worry about in the RISE Lab? You probably remember this picture from our RISE Lab slides that you've seen many times. What this picture is basically just the pipeline of making decisions. So you have a bunch of devices or users that produce data, and this goes into a preprocessing stage that eventually some computation, some data gets stored, and then this is used in a decision engine that then, again, users, devices could query and get decisions back. So the problem is that security threats can occur at every single level in this pipeline. And they occur because a few security properties are violated, such as one is authorization. Basically, only authorized users should be able to control certain devices. But I'm sure you heard about all kinds of bad situations in the news, such as, for example, a hacker managing to control the Jeep of a person and stopping it on a highway. Okay, so the problem happens that decision is pushed by a compromised party. Then we worry about violations to integrity. So by integrity, what we mean is that the data in the computation should run in a way that's not changed by the attacker. And we heard about violations to that as well. So for example, a very scary one is when attacker pushed bad data to an engine that then pushed decisions to a pacemaker. So for example, a doctor was reading this data and pushing its decisions on the treatment to a pacemaker, and hackers basically demonstrated how they can kill patients that way. Then we also worry about attacks to confidentiality, of course. We hear about data breaches all the time in the news. The point is that some unauthorized person gets access to sensitive data. For example, medical healthcare, the latest breach was quite recently, last year. Okay, but we hear about these breaches all the time, and the problems can happen at any stage when it comes to confidentiality. When you store the data, when you pre-process it, when you decide, there could be confidentiality issues of the model, of the decision, of the data, of the computation. And then we also worry about robustness to attackers, right? So the property that the learning algorithms should be resilient to adversarial input. Okay, so probably you remember the case of the Tay chatbot that got tricked by people to start discriminating. Okay, so you can see through all these examples that the attackers can intervene at any step and they can violate these properties. So what kind of properties do we care about in the RISE lab? Well, actually all of them. Okay, so when we refer to a secure decision stack, ideally that stack embeds protection for all of these properties. So right now, I'm going to give you an overview of the most recent projects in the lab. Okay, so these are the projects within the last year or two, and they cover every single one of these properties. For authorization, we have Wave, and you will hear about Wave today. But any project involved, you will hear about at this retreat. For integrity, we have Verena and Dizik. For confidentiality, we have a bunch of different works, and that's because confidentiality is a very tricky aspect, and it has different shades, different models, different guarantees. So you're going to hear about Opaque, which is a data analytics framework, EOS, which is for searching on encrypted data, Chorus, analytics with differential privacy, and SafeBricks for network security. And then for robustness, we have a bunch of work in the lab about adversarial learning, making the algorithms robust to adversarial input. And you're also going to hear about this on Wednesday. So our goal within the security side is also to produce open source artifacts and to embed them within the rest of the RISE platform, so within Ray, Tegra, Spark, Drizzle, and others. So for example, Opaque is a data analytics framework that has security built in, and that builds on top of Spark SQL and is also open source. So I'll be frank and say that insecurity is much harder to have impact and get industry adoption. We know of classical solutions that have been there for a long time, such as SSL, access control, and intrusion detection. These things are widely adopted, but the more modern security that has been studied for the past many years hasn't really been making it into adoption. And we really want to change that, right? Because that kind of security is very expressive, gives us all sorts of wonderful properties. But it requires a very careful understanding of the performance of your system, of evaluation, deployment. So we really need your feedback for this. Okay, so we need you to give us feedback on what are the most burning security problems you worry about, feedback on what we're doing, and any kind of input. Use cases would be very helpful. Okay? All right, so in the next few slides, I'll give you a very, very high overview of each one of these 4 categories and what is our approach within them. And then you'll hear more details when the students actually present the respective projects. So in Wave, Wave is a publish and subscribe syndication model for Internet of Things. The purpose is to give you authorization, okay? Authorization and authentication without a central authority. Okay? You don't want to rely on a central trust for the various IoT devices that can affect your life or that can monitor your private data. And how do we do this? How can we obtain authorization without trusting some central party? And here the insight is to leverage the blockchain microcontracts in order to obtain consensus on who has permissions to control what, on revocation, and also for DDoS protection, which I'm sure you heard about some recent incidents. Okay. And this is also open source. For integrity, the idea is that, let's say we have a cloud compute some long-running computation for us, and we want to make sure that the result is correct. Think about a model in machine learning. It may have taken very long to train that model, and then you want to make sensitive decisions based on that model that affect someone's health. So the question is, how can you check that the model or the decisions, the result of the computation is correct? And our approach here is that we're going to let the computation run at the cloud, but then we're going to verify the result efficiently without rerunning the computation by having the cloud give us a proof that the computation happened correctly and that we can efficiently verify. So we have two projects within this space. One is specialized and the other is generic. Verena is specialized to web applications and in particular SQL type queries. And the idea is that when you load the web page, you can really make sure that the contents are correct, were only changed by authorized people, including the results of computations and of queries. And this particularly helps with the pacemaker problem, where the pacemaker gets updates from a doctor that has viewed statistics generated by a potentially corrupted cloud. Okay, and the other project, DZIC, enables arbitrary computations to be verified efficiently. And this is really mind-boggling because you can run a computation for a year, but you're always going to verify it in less than 5 milliseconds. And this relies on some very crazy and cool theory, the theory of zero-knowledge proofs. Okay. Then for confidentiality and privacy, we have multiple approaches, and that's because this is very difficult property to provide with different shades, different system models. So the two directions are to compute on or with encrypted data. So keep your data encrypted for as much as you can and then compute with it in that state. And the other is differential privacy. So for computing with encrypted data, we have two approaches. One is using cryptography alone. That's more specialized in what functions it can support efficiently. And the other is using hardware enclaves, such as Intel SGX, that is more generic, but makes this hardware assumption. So let me give you a sense of each one of these approaches at a very high level. So computing on encrypted data, the idea is very simple. You have your client or devices that generate secret data. This data gets encrypted with a key that is only on the client, so not on the server side. The data gets sent encrypted to the cloud. The cloud can compute on it using the properties of the encryption scheme, so computes on it, keeping it encrypted without being able to decrypt. So the attacker only sees encrypted data. And then returns the encrypted result to the client who can decrypt. The advantage of this approach is that it reconciles confidentiality and functionality. And here we have two projects in the lab. One is ARCS that can do SQL queries on an encrypted database. And the other is Blindbox Embark that can do network processing, such as intrusion detection, firewall, all while keeping the data encrypted. In the hardware enclave space, such as Intel SGX, the setup is a bit different. The idea is that the client sets up an enclave on the server side in which the client's key resides, and using this key, the enclave can decrypt the data and compute on it as normally. That's why enclaves can support any functionality you want. But the nice property they have is that an operating system can only see encrypted data. So even if it's compromised, even if you compromise the software stack, these kind of approaches help you. Okay? And then the result is encrypted by the enclave and sent encrypted back to the client who can decrypt. And we have a few projects in this space. One is OPE for data analytics and machine learning, and SafeRIX, which is for rich network processing. And also, I should have included EOS here that we're going to hear about a talk today. Okay, in terms of differential privacy, this is a very complementary approach because the setup is different. The setup is that the server actually has the data, decrypted. And the clients want to query the data, I want to get some results, but the server doesn't want to tell the data to the client. So the server has to be careful what it returns because that result could leak about the data. So using differential privacy, it adds noise. And the noise, hopefully, is small enough that the result still is very useful, but at the same time protects the privacy of individual records in the database. And for this, we have two projects, Allegro and Chorus, that give you differential privacy for data analytics. And you're going to hear about Chorus today. Okay? So for the third property, which is adversarial learning, the idea is that you want to make both the inference phase and the learning phase be resilient against adversarial input. So in the inference phase, the attacker may attempt to craft queries so as to get a decision that the attacker wants. For example, in this case, the same model inferred these two pictures, one as a stop sign, one as a yield sign. And that's dangerous, for example, for automated driving. In the learning phase, the attacker could try to disrupt the model by providing malicious data. Okay, so how do you make the learning algorithms resilient to that? And we have a bunch of work in the lab on this topic, and Chang is going to tell you more about it. And it comes from as a synergy between deep learning and security. So on the deep learning side, Chang has some work on creating adversarial examples that are black box that basically manage to trick a model to make a wrong decision. And on the security side is about how do you actually use the machine learning, the deep learning for security, such as for vulnerability detection. Okay, so by this I give you an overview of the recent efforts in security which cover all these properties. And we have some very interesting new directions, such as privacy in IoT, such as private and more intelligent network intrusion detection, federated learning and analytics on encrypted data, and various continued work on the projects you saw that's not just incremental, but really adding different dimensions to it. So before I conclude, I'd like to just draw your attention to one of them because we really need your input here, and that is federated learning analytics on confidential data. So the idea is very simple. You have different parties that have sensitive data, like hospitals, they have sensitive data. They're not allowed to share it with each other, either because of privacy laws or privacy concerns, or in the case of you companies, because of proprietary data. Okay? So these parties could be anything, could be hospitals, companies, divisions within companies. And they would really benefit if they could run this computation together, okay? If they could run some learning over everyone's data instead of just over their data. So we're looking into enabling this to happen with confidential data. So the idea is that you send the data encrypted to some other party. This party cannot tell what the data is. And then you do the computation in the encrypted domain and learn a model over all the data. Okay, you either do it using encrypted data or using hardware enclaves. So we're contemplating different approaches. Wenting is going to tell you how to do it using hardware enclaves in opaque. But we're also considering cryptography alone, such as secure multi-party computation. Okay? And the advantage of this is very promising is that the parties get the result, they can decrypt them, or whoever they want can decrypt the result. But in this process, no one learns the data of another party. Okay, so party 2 learns only the result, but doesn't learn the data of the other parties. And so for the cloud. Okay? So this enables sharing of confidential data that before could not have been shared. This enables more interesting studies or more interesting applications. And we really need your feedback here because our techniques could support a variety of setups, and we'd really like to know what system is it the most important to build? What use cases do you have? Who is going to be decrypting? What kind of computations do you have in mind? Okay, and even actually some help with what's the right name for this. Shared learning, federated learning, collaborative learning, and so forth. Okay, so we'd really love to have your feedback here. So please come and talk to us, talk to me, talk to the students presenting security, talk to anyone. Come to the shared learning tables and give us some feedback on this. Okay, So in conclusion, these are the various efforts we have in the RISE Lab currently in the security space, and they're pretty much, as you can see, blends between system security and machine learning. And the ones in bold you're going to hear about during this retreat. Thank you.
So next, Michael Jordan requires no introduction. He's going to give an overview on AI and machine learning.
Come on, help me find the, yeah, there we go. Thank you. On that right side. Looking good. Usual problem. You know how to do it? There we go, thank you. Okay, welcome everybody. This is the 45th retreat I've been to. Right, so a couple of things to say about this slide. First of all, I use the word ML. I noticed in Jan's presentation, he doesn't say ML anymore, he says AI. And so it's funny how this happened, you know. There's all this wave of activity in this field in AI, and it's all ML. There's no new discoveries in AI. It's all machine learning. But somehow, the press or Google or whoever decided it's going to be called AI. Suddenly, you know, for whatever reason. It sounds sexier, sounds bigger. But just be aware of that. That's really all that's changed is that we have more data and our ML algorithms are working better and better, and so people are now calling it AI. I personally don't consider it particularly intelligent. It's pattern recognition, it's pattern matching, it's instrumentation, it's all the things we've been doing in the past, which is not that super intelligent. It matches behavior it sees in the world. And all this glamorous talk about AI in the future and all this and super intelligence and all that, just nonsense. So just I like to say that occasionally because not enough people seem to be saying it. So that's one comment. The other comment is that this is not really ML in the RISE Lab. I will continue to work on ML for my whole life, but now everybody else is working on it too, and that's great. So every other person up in that picture, I think, has a serious ML effort. And so I won't be overviewing everybody's effort. Maybe later, I think one of the fun things about these retreats is that as 2 or 3 years go by, we start to see emerging themes and how we bring them together and thread some kind of a story that links them all, and that's really fun to do. So in this kind of early retreat, I'm just going to talk about some things that I'm interested in right now that my group is focused on, trying to get at some fundamental issues. I always kind of try to go for the fundamentals and what's really not understood deeply and see if we can get that, and that'll hopefully then spark work in systems. So I'm going to just mention 3 themes or projects that have gone somewhere. One of them is theory of error control for multiple decisions. So this is a fundamental issue that's still really unresolved. If I make one decision, it's kind of very classical work going back about 100 years on how to control errors in that situation. You know, it's hypothesis testing. But we almost always have multiple decisions to be made, and that's the whole focus of this lab. So is there a corresponding theory when you're making multiple decisions? In particular, how are you making the decisions? Are they linked in some way? Are there logical constraints on them? Are they being done over time? Are they online decisions? So all the settings in which we make decisions, how can I control the overall error rate in that kind of setting? And you've heard about this sort of thing when you think about replicability crisis in science. You know, people are making decisions on their experimental data, and the total number of decisions seem to be, the error rate is not being effectively controlled in science. I'll just allude to a later talk on convergence rates for non-convex optimization. That is, of course, the very important area right now driving all of this ML/AI research, non-convex optimization. And Chi-Jen in the audience is a world expert on that at this point. He's going to talk about saddle point avoidance, which is kind of the core optimization problem there. And then I want to say a little bit about where we've gone just sort of yesterday. Down in my garden, my collaborators and I sat down and worked on this some more on gradient-based optimization. What are the fundamental lower bounds? How fast can you possibly go? So if we're going to talk about real time and how fast you'd like to go, how fast can you possibly go? We don't want to overpromise. Okay, so let's talk a little bit about this. Classical hypothesis testing. You know, Neyman Pearson, Neyman at Berkeley developed this theory of controlling the error rate of making a false positive and then trying to make sure you don't make too many false negatives. That's classical hypothesis testing. Tukey, who invented the FFT and a whole bunch of other things in the 60s, initiated this field of multiple hypothesis testing. So ensure that the probability of making one bad decision in a set of decisions is well controlled. It's kind of the way it was formulated early on. All right, now that's very stringent. If I'm making 10,000 decisions, the probability of making one bad decision is going to be kind of big. And so people did work on this. There were algorithms, but they were often too conservative. They didn't allow you to make any discoveries. And so they were used, but they were viewed as too conservative and didn't kind of make it into industrial use, let's say. And about, I don't know, 20 years ago now, this new idea came out called false discovery rates. It's really, in some sense, a very simple idea, as most good ideas are, and it's been very important in statistics, and it's being used. So ensure the fraction of errors over a set of decisions is well controlled. So if I'm willing to make 100 decisions in some situation, I don't have to make decisions, but suppose I'm willing to make 100, I want to ensure that only, say, 5 of those decisions out of those 100 I made are bad. The fraction of errors. So this is different than saying that I'm controlling over all my decisions that I don't make any errors at all. All right, so this led to a lot of math, a lot of algorithms, and this has been deployed. The developer of this, Yoav Benyamini, though, notes that, say, in the New England Journal of Medicine, as he plots the number of papers that use FDR instead of classical hypothesis decision over time, it kind of went up for a little while, then it came back down, and then it's even gone down lower. People are just still resistant to this kind of important notion of control. Now, maybe one of the problems is the early work had to make a lot of mathematical independence assumptions and structural assumptions. And the goal of the later research that we're working on here, and many others, but we're really had some real progress lately, is to remove the independence assumptions and let decisions be dependent. Okay, so that's what we're going to be doing, dependent in a couple of ways. Now, I just want to show a little cartoon. This comes from Aditya Ramdas. I think others too, but Aditya showed it to me. He's leading our effort here, and this cartoon he uses in his talks, and I agree. So let's suppose that someone says, jelly beans cause acne. And so someone says to the scientist, investigate. All right, and the scientists say, well, we're playing Minecraft. Okay, fine. And then so they study it, and they find no link between jelly beans and acne with p greater than 0.05. Okay, and they say that settles that. But then someone says, well, I heard it's a certain color that causes the acne. And so the scientists come back again, and they're asked to do it again. So they do a whole sequence of studies, and they find no link between purple jelly beans and acne at p.05. No link between brown jelly beans and acne at p.05, et cetera, for all the colors they keep going and going and going. And they test all these things. And the next day in the newspaper, big announcement. Green jelly beans are linked to acne with 95% confidence. Okay? Because one of those experiments came back, the green one happened by chance alone to deliver this result, and because each one of them was done at 0.05%, naively, you think you're controlling this overall error rate. Okay? So this is silly, but it happens all the time throughout science, throughout the press, and throughout industries that are doing A/B tests and not controlling their overall error rate. Okay, so we got to fix this. Oops, how did that happen? Okay, so here's the definition of false discovery rates. Expected value of the number of false discoveries divided by the number of discoveries. Extremely simple kind of notion. How can you control that? Well, one way to keep it under 0.05 is the following very simple procedure. For each of your possible discoveries, it's a hypothesis. You have a p-value, a tail probability being out far under the null hypothesis. You sort them, all right? And then you walk along, and you've kind of got a line there. K over n is a linear function with slope 1 over n. You walk along until you find the maximal p-value in the list that is less than or equal to 0.05 times that fraction. All right? And then you reject everything below that. So this is called the Benyamini-Hochberg procedure, and it's been studied a huge amount. There's probably 10,000 papers about it. And it really should be used in lots and lots of situations. Just recently, Max Rabinovich, Aditya, Martin, and I, and Max is in the audience, have the first theorem that shows this is actually optimal in a certain sense. It was just known as a procedure that controlled something. But it turns out that it's actually mini-max optimal, kind of interestingly and somewhat surprisingly. All right, so this latest piece of work, we have a very neat lemma. So, to kind of pump it up a little bit, Neyman Pearson lemma was the lemma for false positive, testing. Back some 100 years ago. And this lemma, in some sense, feels just almost as kind of generally useful. So one way of stating Neyman Pearson is that when you look at p-values under the null hypothesis, that a certain ratio is less than or equal to 1 or equal to 1, So T in the denominator is like the uniform distribution, and the one upstairs is your rejection indicator random variable. And so if those are equal to 1, you're like a uniform, okay? So that's just kind of one way of saying what happens to statistical hypothesis testing. So it turns out that this is true even if you allow the denominator to be a random variable. So you have two random variables, one here and one here. You take the expectation. This thing is still controlled. So this is a surprise that there's this lemma is kind of a two-page proof that this happens in extreme generality. So with that lemma, it's possible to go in and look at all kinds of dependent situations where you have control over the overall rate. So I'm going to just show you one to kind of whet your appetite. There will be talks about this at future retreats. Something called the gene ontology, very, very important in biology, is a collection of hypotheses. A protein can be an enzyme or not. That's a hypothesis. So if I just someone gave me a new protein, maybe they gave me the sequence or they isolated it, or cloned it, or whatever, I can ask, is that an enzyme? Is that going to act in an enzymatic way in the cell? So that's a node in this thing called the gene ontology. Below that is enzyme acting on a certain substrate. That's a node there, and that's a hypothesis too. Is this protein an enzyme acting on a certain substrate? Those are logically linked hypotheses. You can't be an enzyme working on a certain substrate and not be an enzyme. So you can't make those decisions independently at all. They're not even just stochastically related, they're logically related. All right? So now, suppose I got some protein and I go and I light up certain nodes in that. You're an enzyme, you're not. You're a membrane protein or you're not, and so on. These are all these collection of hypotheses. And I want to assert a whole bag of them together coherently, respecting logical constraints, but still controlling my overall error rate over that entire thing. All right? So that's been an open problem for about 20 years. All right? And this super uniformity lemma just solves that. It just goes right in and solves that. So that is the sequence of false or discoveries and non-discoveries for a particular protein in a particular experiment that we've done. So a paper has been finished on that, and we will be talking about that in a future thing. So grab me if you're interested in that. The current work is just that. That's on directed graphs, where you have logical dependencies. There's also a corresponding line of work on undirected graphs, where you have your neighbors who are testing hypotheses. And so think about a real network where I have a local view of the world, and I'm connected to my neighbors by a route, a network, and the decisions over there propagate to me, and I make my decisions, and these things flow over. So it's kind of a typical graph flow kind of algorithm, but in the world of multiple decisions and trying to control overall error rates. And probably the most interesting one is one we just submitted to NIPS, which is on online FDR, where my data are coming in sequentially, and I'm trying to make decisions. So at the end of all of my sequence of decisions, the overall FDR was controlled. So that introduced some really interesting conceptual challenges, which I think we've sort of solved. Okay, that was number one. Number two is about non-convex optimization. And really what this means, well, you're non-convex, you don't have a bowl-shaped object, you have possible saddle points, where it's a bowl in one direction and not a bowl in other directions. Of course, you have local maxima too, but the saddle points are the worst part. And if you're trying to do real-time optimization on a surface like that, saddle points slow you down. You're on a gradient, and you start to get close to a saddle point, the gradient starts to go to 0, and you sort of stick there for a long time. And finally, eventually, you find the way out. All right? That could take a long amount of time, especially in high-dimensional spaces, like 100,000 dimensions. Conceivably, that could take sort of forever. And you could be running and running and running, you never get to the final answer. All right? So you might think you have to do Hessian-based methods that find all the curvatures and try to find that direction quickly and get out and all that. And in sort of a miraculous line of work that Chi-Jen has led, and we've had several papers about this, he'll be talking about this. It turns out that gradient-based methods actually do not stay close to saddle points, provably, for long. Okay? They get out in polynomial time, and they get out with a dimension dependence, which is polylogarithmic in dimension. So this is extremely surprising. Previous work suggested it might be polynomial dimension, which is bad. It's not. It's logarithmic in dimension. So that's really striking. Research, I think, is kind of the best research out there right now on saddle point avoidance and non-convex optimization. Okay, last little topic. How am I doing, Jan? 2 more minutes is okay? All right, it's okay. Fundamental bounds on gradient-based optimization. So finally trying to formulate this problem in the right way. What this problem is a kind of a 300-year-old problem that no one's really stated, I think, yet. It's how is there an optimal way to optimize? So the whole literature in optimization has always been, here's some algorithm that we like, conjugate gradient or Langshos or whatever, and here's its convergence rate on some class of functions. And then someone comes up with some other algorithm, and here this is its rate, and it's a little better on this class, and so on. All right? You'd like to eventually say, is there a best way to optimize? And is this algorithm achieving that lower bound? And that arose in the 70s and 80s in the Russian school, and it took kind of the fall of the Soviet Union for those ideas to percolate over, and now they're viewed as extremely important. It turns out there is an optimal way to optimize. An oracle model was developed, and I think of this as more productive than complexity theory in terms of trying to understand computation in the sense of machine learning. How fast can you possibly go? So one of the things they first showed is that classical gradient-based algorithms like conjugate gradient or gradient descent do not achieve the oracle lower bounds. That was a surprise to people. And then, in an amazing line of work, Nesterov discovered a set of accelerated methods that did achieve the lower bounds that are much faster. So this has kind of driven a lot of this latest wave on gradient-based optimization. But this has still been viewed as a mystery. He just, by his miraculous genius, kind of wrote down these algorithms. There are discrete time difference equations that really no one quite understands. All right? And so in the AMP lab, one of our success stories, which we didn't quite trumpet enough, but we should have, is that we have developed a variational explanation of acceleration. So we now think we understand acceleration in a deep sense. And it turned out the way to do that was not stay in discrete time. You had to go into continuous time, and then you could develop such a theory. And in continuous time, those difference equations become differential equations. And so this whole line of research has been studying a new class of differential equations. Okay? And so this is interesting because differentiation and integration are linked in many, many fields. Physics and statistics, Lagrange's, Hamiltonians, Laplace, saddle point, and so on. The numerical disciplines are full of links between integration and differentiation. Optimization has not been. It has been all about differentiation, gradients, Hessians, and you never see an integral sign. And so this line of work is saying that it's actually integration is going to come in a very, very important way. These differential equations arise variationally, meaning they're can be written in terms of an integral, and the whole problem becomes discretizing a certain set of differential equations that are formed by an integral. Okay, and so there is an area that's about 100 years old called symplectic integration, and it's about discretizing, putting on a computer, systems of differential equations obtained from physical principles. Okay, so if you want to simulate the cosmos or simulate a protein, there are equations, Einstein's general relativity or quantum physics equations that lead to some differential equations. If you were to simulate them in a naive way, just kind of hopping around the curve looking at the gradient, you would get an approximation and you would bleed away energy or momentum. You wouldn't do the real physics. So you'd like to ask, is there a discretization methodology that exactly conserves momentum and energy? And that was worked out by Hamilton, Jacobi, Poincaré, and a whole bunch of other people. And there's now about 100-year literature on this, which is amazingly deep. And no one outside of that field seems to know anything about it. All right, so I'm going to cut now. I'm going to stop now. But just to say the answer, we figured out that this is what acceleration is. It's symplectic integration, roughly speaking. And that's an amazing connection. So I can give a whole long talk on that, which I will at some future retreat. But you go to these differential equations, and then symplectic integration is a way to go as fast as possible along a differential equation while being stable. And if you go too fast, you lose stability. And that is exactly the secret of acceleration. So let me just show you a couple of pictures. This is symplectic integration of a particular cost functions we're going down. Notice these methods don't just go downhill, they oscillate. Here's with unstable step size, really large step sizes and small ones. So you sort of get a notion of acceleration. Let me go to the end here. Right, here it is. This is my last slide. So here is Nesterov. It's that darker curve there. And this new method, which is symplectic, it's not exactly just, it adds a little bit of a gradient near the end, just to tell you the answer. And it's just as good as Nesterov and even a little bit better. So no one has beaten Nesterov in this kind of worst case sense or average case sense yet, and this does. And on the weekend, we don't have the curve yet in a PDF, but we're able to shift symplectic over by about a factor of 10. So we're actually now significantly better than Nesterov. And these are still meeting the worst case bounds early on. The rate they eventually achieve is the same, but this is actually a better algorithm and it has principles behind it. So I went on a little long there, but sorry, I wanted to give you a little flavor of kind of some exciting new research we've been doing in the last year that it's sort of off the systems side, but the whole goal of this lab has always been to try to reach far into fundamental mathematical principles and machine learning ideas and reach into systems and try to pull these two things together. And so I think lower bounds and mathematical concepts are really what's needed here. So thank you.